All right, good afternoon, everyone. We are the Living Building Challenge, and our whole entire project is based around creating a net zero water energy system on a net zero energy budget. And we are currently in the gate 2 step of our design. So the whole idea is the problem at hand is that our home water cycle now affects the health of the Huron River. So a lot of the wastewater that is being treated in the plant in Ann Arbor is not able to handle all necessary pollutants and particles that are stemmed from our wastewater. And we have a lot of impervious areas that leads to low quality runoff, and a lot of that runoff is being placed into the Huron River.
So our goal is to move away from the linear input-output system where we take in 75 gallons per day and all of that goes into black water. So we want to take some of that black water that is actually gray water and treat it and pump it back into the house so that we can reuse some water. And as I said, we use 75 gallons per day and all of that is turned into black water. But we want to retrofit the house so that we use 32 gallons of potable water per day, where 2 of those gallons actually turn into black water and 44 of those gallons are gray water, and then we can treat that water to get back 21 more gallons.
So to give you an idea briefly of the design inputs and outputs we're working with, we're working on an energy budget of about 500 kilowatt hours. Our water collection area, which is currently the main roof, the kitchen roof, and the front porch roof, totals currently 925 square feet, and we're hoping to increase that. And then we're also considering the reclaimable water from the gray water used in the house that can be reused in other fixtures, as well as the storage capacity of rainwater and possible additional collection services. So for the outputs, we have a water demand for the gray water of up to 30 gallons per day. We're looking at flow rates for that gray water of about 10 GPM, and then PSI of at least a pressure of at least 20 PSI. For the potable water, we're looking to use about 40 gallons a day, flow rates of 10 to 15 GPM, and again, at least 20 PSI of pressure. And then most importantly, is the potable water has to adhere to EPA standards for drinking water. And then the water that's being reused and also then disposed of as black water has to adhere to the NSF standards. So we'll look first at the water collection and distribution aspect of the system. Gotcha. All right. So in front of the house and on the sides, we have trench drains and rain gardens that are designed to manage stormwater runoff in the property, as well as in nearby properties. In the gray 1, 2, and 3, you see the collection services, intermediate transport, and then storage and distribution of water that we currently have. And in the tan, we'll talk about some of the projected, maybe additional collection services and distribution that we're looking at. So looking first at the rain gardens and the trench drains, we sized the trench drains based on the expected runoff coming down the sidewalk pavement. And then at number 2 here, you see a diagram of what a cross-section of those trench drains looks like. The water from the sidewalk falls into the trench drains and is passed to the rain gardens on the property. We're looking to increase our energy budget a bit by adding some solar panels on the shed on the property. And on the roof, we're looking at replacing the roofing material. So in an initial test, we've seen high concentrations of lead in the rainwater, and which we later determined was coming from the asphalt shingles on the roof. So we'll be hopefully replacing the roof material, and you see a few price estimates there on the table on the top right. We'll also have gutter guards, and you see some gutter and downspout sizings in the bottom right. So the trench drains and rain gardens were sized based not only on the stormwater runoff from this property, but also properties uphill and sidewalk uphill. So on the map on the left, you're seeing a color coding of the regions that are being accounted for, which are the sidewalk uphill, as well as some of the yards uphill, and then the yards in front and sides of the house. And so the rain gardens, the trench drains that we mentioned feed into the rain gardens, and those are sized to accommodate all the areas you see on the map. So this is just a little illustration of what a rain garden looks like. It's just a depression in the land that's absorbing stormwater runoff so it doesn't run off into storm drains and then into the Huron River eventually. The picture here is the front of the house before rain gardens were installed, and then last September we constructed 3 rain gardens on the property, and so you see a few photos here of what those look like. Okay, so the rainwater storage, collection, storage, and distribution break down as follows. So at number 1, you see our collection surface is the roof. Number 2, we looked at the gutters and the downspouts that are feeding from the roof to the cistern. So number 4 is the cistern, and 5, we'll look at the distribution to the rest of the house. So starting with the roof, we are planning to use the existing gutters for now, but we'll be adding gutter guards that keep out some leaves and other large debris. And you see the gutter sizings here on as I'm marking with the cursor. So from the gutters and the downspouts, we'll have an adapter that feeds into piping. So we'll note here that we aren't allowed to use PVC piping due to its environmental effects during manufacturing. So the piping you'll see here on the diagrams, we're looking at polypropylene for supply outside the house, and then eventually PEX and polyethylene as other plastics used in these components. So from the downspouts, we're feeding into polypropylene pipe. The water will pass through a pre-filter, which removes some additional debris from the water and then into the cistern. And then from the cistern, we supply the rest of the house. So here you see some calculations how we decided to size the cistern. So this graph on the left is showing the catchment area versus, as well as the cistern size versus the number of dry days we would expect in 1 year. So a couple notes to take away from this. The first is that with our current catchment area, there's not much difference in the size of the cistern. It doesn't matter what size cistern we use. However, if we can increase our catchment area by 25%, then we see a significant drop in the dry days. And for that 25% amplification, we see that a 2,500 or a 3,000 gallon cistern would be about equivalent as far as the number of dry days. So we're currently targeting a 2,500 gallon cistern. As far as the location of the cistern, we don't have enough space in the basement of the house, so it's going to be buried underground outside the house. And that was, as far as where outside, we had to take into account a geothermal field that's currently being used at the house, so we have to avoid underground, as well as the ground that's supporting the foundation. So it has to be placed a certain distance away from the side of the house. So for the distribution aspect of the rainwater, so from the cistern at number 1, we have a 1 horsepower pump that's pulling water from the cistern at number 2. It feeds to number 3, which is the purification system. From the purification system feeds number 4, which is a pressure tank, which then feeds pressurized water to the rest of the house. So some details on each of those components. I talked about the pre-filter in the cistern already. The pump was sized based on the pressures we need in the pressure tank, as well as some pressure drops that we see in the purification system across some of the filters. And so I'll move to the pressure tank as to why we're using a pressure tank. To avoid having the pump run multiple times a day for large portions of the day, we can save energy and also increase the lifetime of the pump. So this was what the pressure tank is for. The pump will basically pump once or twice a day to fill the pressure tank, and then the pressure tank will supply pressurized water to the house the rest of the day. So we have a little simulation here of the expected water usage in the house as flow rates, and that's here on the left. And then on the right, you see a plot of when those demands are at different times of day. And so in the bottom right, then you see this is a simulation of the water level in the pressure tank as the water is used by demand in the house and then refilled by the pump. So we estimate that given these predicted usages in the house, we can pump once, maybe twice a day, and that'll be sufficient.
So now we can move on to the purification part of our project. As you can see from this graph, we have collected results from testing our water. The beige columns are from information that we found in a journal. However, we can pay attention to the other 2 columns, which show results that we have tested from. So As you can see, we are below EPA standard for almost everything, but our main concerns are turbidity, lead, and coliforms. Turbidity is easier to remove. We can remove that through filters, and our coliforms we can remove through UV bulb disinfection. We have to pay attention to our lead problem. The lead, we have concluded, comes from mostly our shingles. The EPA standard for lead is 0.0 parts per million, and then the concentration in runoff is 0.04 parts per million, which is 4 times more than the EPA standard, and the concentration from atmospheric deposition is 0.004 parts per million, which is one order of magnitude less, and we calculated that from using the deposition velocity. We're not 100% sure what our deposition velocity is because that depends on what the weather is and wind and everything. So we created a range of what our concentration could be. So it could be anywhere from 0.0027 to 0.004 parts per million. And our concentration from our shingles is 5 orders of magnitude greater than the EPA standards. It's around 513 parts per million. So it's a lot larger than what it should be. So that's our main concern. So this shows how we will solve to meet each EPA standard. So for turbidity, we'll use mesh and cartridge filters. For the chemical oxygen demand, we'll use the activated carbon, and for lead also we'll use activated carbon, and for coliforms we'll use our UV disinfection bulb. That'll help us meet our EPA standard. But the main thing is that since we have so much lead in our water, we need to possibly change the roofing material, and that will help reduce our maintenance costs by a lot because we wouldn't have to change the activated carbon as frequently. So that'll help reduce that cost.
Now we're going on to the wastewater management part of our system. So one of our main areas of concern was kind of replacing the toilets that are now in place in the residential household into new composting systems. So we've highlighted 3 different options that kind of, we wanted to look at the water usage and the energy costs and also the implementation for each system. And we kind of highlighted the advantages of each. And based off of that, we've concluded that the option 2 that we found, which is the Sunmar company, has the best advantages that we're looking for in terms of cost and also the amount of water that is being used. A huge part of our focus for wastewater is to make sure that the quality of our water is kind of being addressed. We have the blue areas highlighted in this diagram, which is basically every single water that isn't being touched by the kitchen sink. And this red part is the kitchen here. And the graph on the left-hand side shows the target levels that we're looking for in order to either reuse the water within the toilets or also discharge out into the outdoor irrigation. And the squares represent the outdoor irrigation targets, and the triangles are the ones of the toilets being reused. This is kind of an overview of this portion of our project. We have the different sources of gray water and black water, and then this kind of shows the flow rate and also the volume of the water that our system needs to address in order to properly discharge them out into our systems. All of the water based from the dishwasher and the kitchen faucet are going to be going out into the engineered wetland, and the excess coming from the hydroponic system is also going to be treated through that method, of course. So when we're looking at different technologies to use, we compiled kind of a list and kind of crossed off ones that we felt that weren't really matching what we were looking for. So here we ruled out any technologies that basically weren't necessary. So an example is an ion exchange because we have no heavy metals that are included. And in addition, the API oil water separator isn't really necessary because we're thinking about implementing a grease filter in our purification system. So we further narrowed down our search by ruling out technologies that we thought were too big to implement in the size of what we're working with. An example of this would be the flocculation and sedimentation, which includes a batch tank that is really too large to be used with the size that we're working with. And lastly, we ruled out technology that was too energy intensive. So something like a vacuum evaporation would just be require too much energy to use. So we decided to use a hydroponic system which uses a combination of technologies from a bioreactor and a trickling filter. And these two diagrams kind of lay out the processes that the hydroponic system will take. A key advantage is that it is inside the house, and it does have some aesthetic value to add. Some of the mechanisms at play within our hydroponic system, you can see that certain things like aeration or nitrification take out certain particles. And based off of those mechanisms, we can then decide which layers we can use to be applied within our hydroponic system. So you can see the graph and the table on the left kind of show which mechanism matches with which layer. And lastly, we have a few examples and prototypes of the hydroponic system and also the engineered wetland that we've been looking into. We've calculated the size of the wetland that we'd need in order to treat the amount of black water that we have. And we've noted that it should be a subsurface flow engineered wetland.
All right, so here you're looking at just a summary of the cost and the energy budget for the project. So really, we'll just focus right now on the bottom here, the totals. We're using about 500 kilowatt hours for the system, and we're looking at a cost of about $38,000.
Now we can move on to some concerns and restrictions that we may have. So our number one concern is the health risk from rainwater collection, purification, and gray water purification. We need our designs approved to meet the standards from the county and the city, but because our goal is to shift the liability from the city to the homeowner, and we need to reduce our risks associated with this project. And another challenge that we might have is getting our rainwater collection, gray water system, and black water systems approved. We can do this by applying for variances separate for each one separately. However, we may get those variances a couple years after implementation, so even though our system is implemented, we would have to wait a couple years for it to be fully used until we get our variance.
I wanted to briefly mention an outreach effort working with the Mapuche community in Chile. And they're building a community center, and they want to have a rainwater harvesting system there that will supply drinking water and irrigation water. And so we passed along the spreadsheet that we use to calculate our cistern size. We use that to help them with sizing their cistern. And so here in the graphs you see the cistern levels over time, and also the precipitation data that's based on.
So thank you for listening to us. Does anybody have any questions or comments?
When you're talking about the gray water, you had the kitchen sink by itself. Was that, were you looking at the water coming, like going into the drain and then like using it after the kitchen sink, or do you mean the water coming out of the faucet and using in the kitchen sink?
I think we were talking about the water that's leaving like through the drain is going to be output into the engineering wetland. So we're just going to treat that water because we kind of view that as black water. We're not going to be trying to reuse that. So we're just putting that out into the engineering wetland.
So could you repeat that? Everyone in the audience will be happy to take questions as well.
So a few questions ahead. So for it was earlier on in the presentation, you were talking about the potable water with, so I guess with the gray water, why does that need to be potable and at the pressure level for potable water when being used in the house?
Sure.
So actually, it doesn't have to be potable, but there are standards as to what can be reused, a certain quality before it can be reused. And specifically, we're reusing it in the toilets and in the washing machine.
Okay.
So we have slightly different pressure and flow rate requirements. They're very similar, but they're depending on what those fixtures need.
Okay, so did you just use was it 20 PSI for both of them? Just to make things simple, or is it not like a set PSI? Like
So We
Oh,
need to
okay.
supply 20 psi to the washing machine. And also for the potable system, we have to supply definitely greater than 20 psi to the farthest shower in the house. So they just turn out to be the same.
Okay. And then for the budget, I guess at the very end it had like estimated totals. So what was your limiting factor for the total budget cost? Was it based on funding that the team had, or funding that was required by Matt, or I guess what was the limitation with that?
I think Devki.
Oh, sure. Well, Barry and Hannah, do you want to talk about the differences with BLUElab too?
Yeah, so we got 2 grants, which is great. We have the Ford Community Challenge grant, which was, I think, $25,000. And then we have a grant that Daria actually applied for, the Dow Sustainability Grant. And so total we have $40,000 in grant money that actually expires at the end of this year, and then like disappears into space. And so we'd really like to use it. And that's where kind of the maximum limit came from. We'd like to not go over that, obviously. But the cost that we came up with, for the most part, were independent of what the limit was. It was what's the best system that's going to meet all of the requirements we needed to and be safe. And we just so happen to also be under our budget. So that 40 grand is money that's coming from those grants. I don't know if Matt's family will be buying any of those.
They were planning to
things.
chip in $5,000, but then they got a surprise baby. So was that recorded?
Well, okay, and then my final point was about the Mapuche people. So I didn't quite understand how the cistern size was calculated.
Oh, I'll pull up the system size in here.
Slide 38 there.
Okay. And actually, it's using the same calculations as we use for our own cistern, which is, let's see, up here. So basically, what we do is we take a given cistern size and a certain catchment area. So the catchment area is giving for a certain precipitation, it's going to give a certain collection amount of water collected for a certain rain event. So this is basically just plotting, it's as rainwater comes down, it's filling the cistern. As you have needs in the community center, it's depleting the cistern. And so at some point, the system's going to be completely empty, and we call those dry days. And for us, we calculated the number of dry days we'd see in a year. But we used a similar, I don't know if that was what they're interested in.
Yeah, we were just doing dry days based on year. When they're going for the LBC certification, you have to choose which year you want to be monitored for. But it chose a year like, I believe it was 2011, it was really rainy. Is that correct? I think it was probably 2011. They would have been fine that year based on our simulations, but like 2010, they would not have been fine. They would have maybe like 20 dry days. The interesting thing we found, which is like a recurring theme in engineering, we're realizing is that if you want to get to like 90%, 98% of your requirement, like we can have 5 dry days a year or something like that. That'll cost say X amount of dollars. If we want to cover those last 2%, the price is going to go up exponentially.
Yeah. So you can.
Sometimes you want to just shoot for like that 98%, 95%. And another note here is that if their cistern is dry, it doesn't mean they won't have water. They'll also be hooked up to the city. So we would have, there's a floating valve on the bottom of the cistern that shuts off the pump when the water level's too low, so you don't kill the pump trying to draw from an empty cistern. But you can also use that information to switch between city and rainwater where we would have a valve. Technically, that would, you're not supposed to do that in terms of the living building challenge, but it wouldn't really make sense to take them off of city water just from a resiliency perspective, so we would definitely leave them on.
I just had one question about what kind of maintenance do you have to do on the storage tanks and the filters?
I think that's.
I can say for the cistern, people typically have to go and empty it and clean it out about every 5 years.
And like for the composting system, I think our system specifically needs maintenance, I think every year. if there's excess use, then we'd obviously have to replenish the composting material.
And for all the filters and the activated carbon, it's just based off of, the activated carbon will go for you have to change it 2 times a year, but that's also based off of how much lead there is and how, yeah. And then the UV bulb based off of how long it will last.
And the UV bulb, for safety reasons, will actually tell you when it needs to be changed. When it has dropped below the level at which it will continue to kill everything that it needs to. So that if it drops below that level and you don't know it, you can automatically switch to city water so that you're not getting water that's underneath those standards without realizing it.
The reason the UV bulbs have those alarms on them is because the National Sanitation Foundation requires them. They're actually located in Ann Arbor, close to our campus, but they set the standards for the whole country. And for any other teams working on gray water, you might want to download their NSF 350 and NSF 350-1 standards, because those tell you the concentrations you should shoot for if you want to reduce gray water. Yeah.
So that's good. So there is an indication if something does go wrong, they're not drinking. It doesn't take them to get sick, or it doesn't take a person to get,
For them to realize.
Yeah.
taste water. There is systems that you did implement that say, this is not good water, something went wrong.
Yeah.
Like if you lose pressure maybe, is that?
And there, yeah, that's some additional things that we may have to, when we're actually implementing, is pressure gauges after filters to,
That's
a large drop in pressure is an indication of